So I'm the executive director of KB265, and what we do, and this actually goes back to my years here as a graduate student, where I started combining different disciplines. Back in the 90s, it was web development and graphic design to produce tools that would communicate science, scientific illustrations, and so on. And that led to actually create these, we call them science and symphony films, where we present scientific content in a non-traditional venue when it comes to science communication. Because you don't go to the concert hall to learn about science, you go to listen to music. But using music, we can present science in a very non-intimidating way. Art is a great vehicle to engage audiences, both the visual arts, photography, filmmaking, as well, of course, as music. So this project started with a film for Gustav Holst's The Planets, which actually was presented with the University Symphony in last January at Hill Auditorium. And the success of that project led to other productions and to the foundation of KB265, which, by the way, because sometimes I forget, KB265 is, you music buffs might recognize it as a Mozart work, like the Requiem is 626. So 265 is the piano variations that were later used on Twinkle, Twinkle, Little Star. So there you have the intersection of music, science, and popular culture. And of course, I'm a big Mozart fan. So like I said, it started with the planets. To create something that will take away from the music. You want to do something that it's cohesive, and one discipline, the visuals, will reinforce the music, and the other way around. So the other way of putting it is, it's like a soundtrack in reverse. Holst wrote the music 100 years ago, and then it's up to me to create a film that fits the soundtrack, if you will, instead of the other way around. So the fourth production of this whole project was a film based on a children's story called The Legend of the Northern Lights. And that one, actually, we worked with Christopher Theophanidis, a very well-known American composer. And so he actually wrote the music to fit the children's story in the film. So it's like an opera with words. Because of that, then we travel. This is the premiere in Millennium Park, 32,000 people, free concert on two nights. So the success of that film, and because I fell in love with observing and photographing the Northern Lights, led to a second production called Aurora Triptych, using music by John Estasio, Canadian composer who lives in Edmonton. And it led to a commission from Boston Pops to set Respighi's Adoration of the Magi, make a film and set it to that piece of music for a Christmas concert that was presented 33 times last year. So that led me to start photographing the Northern Lights. As part of my science communication work, I do a lot of photography around the world, a lot of astrophotography, a lot of night sky photography of places like where we do astronomy from, like the Atacama Desert. So that took me to places such as Anchorage, Alaska, Iceland, and then, of course, traveling from Anchorage to Chicago. There's always a chance to, I don't miss a chance to photograph the Northern Lights. So this is a time-lapse photography, handheld, 1 second exposure, and just like, you know, put it in time-lapse mode and shot until, you know, my neck hurt because I didn't have a tripod. So I was just literally holding the camera. And then I was able to identify where I was, and this is over Alberta. So can you imagine, I mean, you'll see footage that it will look much more beautiful. Here I'm just pushing technology to its limit. And technology is continuously advancing. I'll show you something more recent that will look even better. But this is, I mean, it's as close to video as I could take, to the point that in 1 second exposure, you'll see the Andromeda galaxy, 1 second exposure. I think I saw the ISO was 10,000, and you'll see comet Pan-STARRS, which was in the field. So I think that will come, that will come next. And you see Lesser Slave Lake and comet Pan-STARRS and the Andromeda galaxy. Okay, so you can see, so aurora borealis means like dawn of the north. You can also see them in the south, aurora australis. And actually, it's kind of like a mirror image phenomenon. Okay, so they're not different. If any, they're very, very similar. But the reason why you don't see a lot of aurora australis images is that if you look at the Earth's globe, most of the land masses are shifted towards the north. So you have Antarctica, and unless you want to winter over in Antarctica as a researcher and stay, you want to see them from the North Pole, then you have to commit to 8 months of your life, because a plane is not going to pick you up or from the South Pole, and of course 6 months of nighttime. So sometimes you can see them from New Zealand and Australia. And of course, you can see them from the International Space Station. As you'll see, the auroras happen in the upper part of the atmosphere, up to hundreds of kilometers in altitude, over the Earth's surface. So the International Space Station actually goes through the upper part of it. It's just that if you look at the orbital inclination of the ISS, it's about 52 degrees. So it's actually kind of like on the lower edge of the auroras in terms of latitude. So personally, after visiting some of these places, I prefer Yellowknife. Yellowknife is the capital city of the Northwest Territories of Canada, with a population of 19,000 people. So, and I'll tell you more about the advantages of Yellowknife towards the end of the talk. But most of the photography, or all of the photography that I will show you that I shot from now on, was shot in Yellowknife. And you can see that you are under the lights. It's not just looking north. And I'll show you a time-lapse sequence, and you'll see how it took only 60 seconds to go from the horizon to the zenith. And then this is, 5 minutes later, it's covering the entire sky. Okay? So, and that happens, on a daily basis. So, there's a connection between the aurora and the sun, because the sun creates a space weather, and we are embedded in that weather, and we're affected by it. So the sun is a sphere of plasma. Plasma is really hot gas. It's so hot that the electrons have been stripped from the atoms, so you have like a soup of ions and electrons. So that means that you have electric currents. Globally, the gas is neutral, but within you have electric currents, electric charges. And of course, the sun is rotating, and it's rotating differentially, meaning that depending on the latitude, it's rotating at different speeds. So when you have electric charges in motion, you're going to create a magnetic field, right? So this is a visualization of the magnetic field, and it goes from, through the cycle, so through the solar cycle, it goes from a very complex magnetic field to a very simple one. And then we have all this plasma, all this material, high energy particles coming from the sun, and this continuous flow of particles. It takes about 2 to 4 days for those particles to travel from the sun to the Earth, which is great, because that means that we can forecast the auroras, right? Because since there's a connection, that's why when you hear that spaceweather.com, for example, says expect auroras at lower latitudes, let's say because the activity is very, very high, you can actually prepare for it. And then you have also these violent events called coronal mass ejections, and you'll see the prominences, you know, those arcs, those loops on the sun. It's actually the magnetic field of the sun itself that otherwise it would be invisible. But how great that when the hot plasma travels through the magnetic field, through the prominences, it renders the magnetic field visible. So let's look at footage shot from NASA, imaged by NASA using the NASA SDO spacecraft, but then set to music by John Estasio. And this is the first part. I'm going to show you the first few minutes of the first part of this work called Solaris. So he was inspired by the sun when he wrote the piece. Since you're all science enthusiasts, that's why you're here. Can you imagine how cool it is to go to an orchestra hall and then, you know, see all these visuals and then stress to the audience that, you know, this is not Hollywood. These are not effects. These are not, you know, it's not done in the computer. Sometimes we show visualizations, which are animations driven by data sets. So everything is science-based. So this is the part of the conclusion of this movement, and we'll see one of those visualizations. So that's the transit of Mercury. So that's part of Solaris. And So we talked about solar wind. We have the coronal mass ejections. Something else that can create and affect the space weather in the way that we'll get more auroras, it's called coronal holes. So corona is the outer layer of the atmosphere, is actually hotter than the surface, millions of degrees. And we're still understanding why it's so hot. It has to do with the magnetic field, and somehow energy is being pumped into the corona. And that's why, to the point that you get iron spectral lines. Okay, so imagine iron in gaseous form. So sometimes the field lines of the magnetic field are open, meaning that they stretch, towards infinity. So they appear as holes in the magnetic field, and what happens is that lets electrons to flow very, very quickly. And again, if that stream is pointing towards where the Earth is going to be 2 days later, we might get brighter auroras. And I say brighter because in places like Yellowknife, you see auroras daily. When you don't see auroras is during the summer months because daytime is too long. So that means that the auroras are there. It's just that the sun is a million times brighter, so you don't get to see the lights during the day. Okay, so the Earth also has a magnetic field, and the beauty of it, remember I told you that prominences and the plasma, it traces a magnetic field. Well, on Earth we have something different, which is the auroras themselves. They trace something that otherwise would be invisible. They trace the magnetic field. So what happens is that in the magnetic tail, many of these electrons coming from the sun, they collect. At some point, it becomes unstable, and there's something called magnetic reconnection, where field lines are going to connect, and that will impart kinetic energy to those electrons, and then they're going to be accelerated from the magnetic tail towards the poles. And as the electrons go through the atmosphere, that's when we get the auroras. And this is an important, distinction, because people say, "Oh, auroras, yeah, it's from electrons coming from the sun." Well, not exactly. The sun is definitely a source. The ionosphere and the sun are sources for these electrons, but you need to collect those electrons first in the magnetic field, because then that's where you have the mechanism to impart enough energy to those electrons to then go through the atmosphere and actually go to lower layers of the atmosphere. You need a lot of energy. The energy that comes directly from the solar electrons is not high enough. And like I was telling you before, that's why on Venus you have this cusp aurora, but not the auroras that we see on Earth, because you need a magnetic field. Okay, so here, another visualization, also from Goddard Space Flight Center. They have a visualization lab, which does wonderful work. So here you see a rendition of the magnetic field, this magnetic line reconnection that I was telling you about. It transfers some kinetic energy to the electrons, and as they go through the atmosphere, then they make the atmosphere glow, and we'll talk more about the emission mechanism. Okay, so you get an oval that corresponds to where the lines are going through the atmosphere, all the way to the core of Earth. The reason why we have a magnetic field is because we have a molten core, we have radioactive decay, we have charged particles, the Earth is rotating, so again, you have charged particles in motion, you're going to create a magnetic field. Okay, but other planets like Venus don't have one. The gas giants, we actually just recently, there was a beautiful image of auroras on Jupiter. And it was a combination of Juno image with Chandra X-ray imaging. So this is a visualization of the aurora oval. So if you are in direct line of sight to the oval, that's when you'll experience aurora. When there is a lot of solar activity and more electrons are pushed through the atmosphere, this oval will grow. So both the north end and the south end will travel. It will expand, but it will travel south. Okay, so to the point that maybe at some northern latitudes, then the auroras disappear because they have migrated to lower latitudes, and that's when we see them from Michigan and other northern United States regions. Okay, so a good analogy is neon signs, which are basically gas discharge tubes. So you have gas, a particular gas, at a very low pressure, and when you run a voltage through the gas, those electrons are going to collide with the atoms or molecules inside in the gas at a very, very low pressure. It will excite the atoms or molecules. That means that electrons that are bound are going to go to higher energy levels, so they absorb that kinetic energy, and when they return to the ground state or a less excited level, they're going to give off that energy as light. Okay, and that's why we can have then neon signs with different gases, and we get different colors. So what happens is that because the energy, the color or energy of the light is dependent on that atomic transition, and I'll show you a diagram of that. The light is not continuous. I mean, the spectrum doesn't happen at any random color. It happens at very discrete wavelengths corresponding to those atomic transitions. Like I said, different gases will provide different colors. So let's take a look. We have here some demonstrations. So this is, the... So we have a neon. So we have a neon sign here, and literally with neon gas. So you see those colors correspond to those particular. You see that it's what we call line emission. Those colors correspond specifically, and then we're getting into quantum physics, specifically to the difference between the energy levels of each transition. Like I said, it's electrons going from excited levels to less excited levels, and then that's where we get emission at that particular color, okay? And as we'll see, that's what happens in the aurora. So that was neon. Then we have molecular nitrogen. Okay, so this is as similar, actually, as we get in the aurora, because molecular nitrogen in the atmosphere is also responsible for auroras, not neon, but molecular nitrogen, and we get both red colors and blue and purple. Okay, and then finally, we have oxygen. The only difference here, the disclaimer, is that this is molecular oxygen. And what's responsible? Sit up. Oh, I'm sorry. I made a step that was not necessary. So we have a camera for oxygen. So thanks, Monica. So here we have molecular oxygen, and the gas responsible for the green and red auroras is actually atomic oxygen. Okay, so so let's look that in detail. So it's like having a natural discharge tube. Now, the confession here that I have to make is that I chose this photo because not only I think it's very, very compelling, and by the way, this is the whole idea behind KB265, to show things that are very compelling, that will get people's attention, and then you can talk, for minutes about the content in the image. So this one, of course, kind of looks like a tube, right? So it gives the impression, it's like, oh, so that means that electrons are moving sideways? Actually, no. The electrons, remember that the magnetic fields are coming from space, and close to the magnetic poles, they're coming, almost perpendicular to the surface. So what we have is a lot of lines going vertically, making this arc, right? So this is part of the aurora oval. So the electrons are actually coming down from space through the upper atmosphere all the way down. Now, this is what we call an homogeneous arc, but then you get something like this, where again, it's another arc. Actually, here we see two curtains, but notice the lines. So the beauty of this is that not only the auroras are beautiful in themselves, but we're seeing the magnetic field of the Earth rendered. I mean, so something that otherwise would be invisible. Okay, so then which gases are responsible for the auroras that we see? As I mentioned, molecular nitrogen, also molecular nitrogen that has been ionized, that is, it has lost an electron, and when it regains the electron, it emits light, and then oxygen atoms. not oxygen molecules, but oxygen atoms. And they have one line in the green part of the spectrum and two in the red. So this is what I was telling you before. So, what better than show a diagram? So we have, an atom with a bound electron. Incoming electrons with a lot of kinetic energy go through the atmosphere. They collide with those atoms. Momentarily, those electrons go to high energy levels. They stay there for a little while. That's called, the radiative lifetime, and this is something that it's measured in the lab. So they stay there for some time, and when they come down, then they emit light that has a frequency corresponding exactly to the difference between those two energy levels, and that's what you get precisely a color of a certain frequency. Okay, so that's atomic excitation. So let's see. Let's start with nitrogen. In this case, is that molecular nitrogen molecular ions I was telling you about. So when they regain an electron, right? So they lose an electron because of the kinetic energy of the impact with incoming electrons or protons. When the ion regains the electron, it will emit light of that frequency, and that's the purple blue light that you see in the background at very high altitudes, okay, hundreds of kilometers above the Earth's surface. Then you have oxygen. Okay, oxygen, the red light we see between 150 and 250 kilometers. So what happens is that here we have oxygen atoms that have been excited. When they go up, the radiative lifetime is almost 2 minutes. So they're going to hang out there for 110 seconds before coming down. So what happens is that in order for you to have that kind of red light, it has to be in the upper part of the atmosphere. Because if you get too close to the Earth's surface, air will be much denser, right? So below 150 kilometers, it's too dense. So what happens is that that electron is hanging out at the excited level, but before it can radiate on its own, it could get hit by another particle and lose the energy in a kinetic way. So it's forced down, but then it imparts that energy to the incoming particle. So it doesn't get to produce a photon. And that's why you have auroras at really high altitudes, because you have this competition between the electrons wanting to come down on their own and the frequency of collisions. Now, for green light, it's actually an atom that has been excited with even more energy, but the radiative lifetime is about 1 second. It's like 0.7 of a second. So that means that green light can occur at lower latitudes, lower altitudes, because the frequency of collisions is less. Okay? So that's why you have a gradient of red and green. So this is a green aurora that is so bright. Look at the ground. It's reflecting that green light from oxygen atoms. And then, of course, if you do the photography in the winter, then snow will reflect all that light as well. So here what has happened is the aurora was about here when I started taking the time-lapse sequence, and then it migrated upwards, and then so it's reflecting it directly into the camera. Okay, so here you see the gradient of red and green. Like I said, red because the radiative lifetime is almost 2 minutes. It has a lower level that is higher than green. So green, what's going to happen is that not only here the air is too dense. By the way, so the lower one is about 100 kilometers or 60 miles. So not only the collisions get more frequent, but you need oxygen atoms, not oxygen molecules. So by then, you need UV light, basically disassociating, right? Splitting oxygen atoms during the day replenishing the upper atmosphere with oxygen atoms, because those are the ones that are going to emit in the green light, not oxygen molecules. So as you come down, there's less oxygen atom and more O2, more oxygen molecules, which of course is what we breathe. So love this photograph because first of all, yeah, the aurora doesn't come down to the ground, right? It's a perspective effect, so it's moving away. But then here you see, so like the lower level of the green is 100 kilometers. The lower altitude of the red is about 150. And then you have the frequencies for those two transitions and the radiative lifetime. So you can see the radiative lifetime of the red is much longer. Okay, so and then these are the atomic transitions in question. So you can get an atom that can, an oxygen atom that can emit green light, because it goes from a very high, highly excited level to a less excited level, and then it can cascade down, right? So it's not just one step, and then it can produce red light. Or it can come directly, more energy, right? Because look at the difference between the two energy levels, so high that the light is actually ultraviolet light. And of course, that would be invisible for the human eye. Then you have nitrogen, what we call the nitrogen red lower border, and this is what you see here. So when the aurora becomes really active and very bright, it's beautiful to see because it's so apparent to the human eye. And I'll talk about human eye perception in a couple of slides. So what happens here is that basically oxygen, the O2 gets, starts to get, oxygen atom gets depleted. So the ratio at that altitude is 4:1 between the nitrogen molecules and the oxygen atoms. So then basically nitrogen emission is going to, N2 emission is going to dominate. Okay, so here you see more of that red lower edge. And another one. So these are, of course, pointing the camera up to the zenith. Okay, so you get the perspective of the red and then, of course, the green and then the red again. This is to me, it was unexpected, and I saw this before actually reading and starting researching the physics behind these processes. But this is beautiful to see. So one of my nights on the second trip to Yellowknife, I was setting up during twilight because I want to be there when the sun sets. I already want to be in place for the most part. And of course, in photography, you might know what's called the blue hour, where it's when you get that deep blue sky, and the sky is not pitch black yet. So it's beautiful for photography. So I'm there ready, and I see auroras already moving, being active. Well, that led to this event where you see this additional beautiful purple, blue-purple color, which is from the nitrogen ion. So what's happening here is that, like I said, you have the electrons and the protons. They hit the nitrogen, the N2 molecule. It ionizes them, right? But then the N2 ion gets at the same wavelength for that transition, gets sunlight at that particular wavelength. So what happens is that it emits the light, and then basically it gets excited and gets excited because of the sunlight absorption. So it goes to the higher energy level and then re-emits, and that's called resonance scattering. So that happens during twilight because why? So it's happening high in the sky, right? So the sunset, for my altitude, I'm on the surface, but at hundreds of kilometers up, it's still seeing sunlight from the setting sun. Okay, so that's why it's only visible during twilight. You will not see it at midnight. So in this image, you see, and again, this is also, like I told you before, what I love to do is just in a single image cram as much science as possible, so I can talk about all the astronomical objects in the sky, and I can talk for minutes just using one single image. But here, what I want you to pay attention to is that not only you have the atomic transitions, but then you have like pink, which is when you have red and blue emission. You can see here the blue emission. Then you get that pink. So that's a combination of looking over the same line of sight. You're combining the red and the blue. And then when you combine red emission and green emission, you get yellow aurora. Okay, so that doesn't correspond to a particular atomic transition, but corresponds to the fact that through the line of sight, you're seeing auroras of 2 different colors. Okay, so for those of you who are into sky watching and astrophotography, this is just to give you an idea of how large of a portion in the sky the auroras cover. So you see constellations, northern constellations. I'm pointing the camera almost, probably just upwards. So look how Polaris, how close it is to the zenith. This is, by the way, this is latitude 62.5, okay, in Canada. And then the diagonal field of view here is 114 degrees. So I really want fast lenses that will capture as much light as possible, very sensitive sensors in my cameras. I shoot with Nikon cameras. And then you want lenses that are really, really wide, at least from this location. Why? Because the auroras are going to cover the entire sky. So let's talk a little bit about structures. Remember that the magnetic field is being continuously buffeted by the stream of electrons, so it reacts to it, and so these structures will change shape. So we have homogeneous arcs, and then we have rayed arcs, so you can see all the magnetic field lines are rendered, and the medium thickness of these structures are about 230 meters. They can be a few kilometers in width. Okay, so of course it varies. And it seems that when it gets brighter, it's like the radiation gets more focused, the stream of electrons. So when they get brighter, actually they get narrower. So the corona is when you're looking at these curtains of light from below. So you get this perspective effect of the lines converging at infinity. And it's a beautiful sight to see. So you get folds in the curtains. You get multiple folds that change very, very quickly. By the way, to the human eye, these. So here you'll see 2 kinds of footage. You'll see time-lapse photography where things are sped up, but I'm going to show you also real-time video. So, but to the human eye, you see the structures changing. You have kinks that last very, very little. Those structures move very, very fast. And then, so these are, what I showed you before, those are discrete auroras, right, because you see definite edges. They go through something called a substorm, where it's a period of activity, and then they become really diffuse. So it's like very disorganized, and it's almost like looking like at an overcast sky. So you might see a little bit of rays there, you might see a little bit of discrete auroras, but it can get completely diffused. And then related to that, you have some patches that pulsate, and then you get pulsating auroras. So the period of the pulses are between a few seconds to 10 seconds, or I think the average is about 10 seconds. So because of that, I haven't perceived them, or I haven't, if I don't know that they're happening, it's hard to perceive. But looking later at the time-lapse photography, where you're taking time and you're compressing it in time, then it's easier to see those pulses. So these are a sequence of a substorm, which is when a rush of, when many electrons rush through the atmosphere at once, they're pumped through, and the auroras start moving really fast, and the brightness goes up. And let's take a look at auroras in motion. This is looking using a fisheye lens. So the circumference is the horizon, looking straight up. Now, this is what I was telling you at the beginning of the talk, that it took about, if I'm not mistaken, I think it was like 60 seconds only, looking at my photographs, to go from that quiet position close to the horizon all the way to the zenith, and then covering the entire sky. So what I'm doing, by the way, every time that I go is I take like 4 cameras. So I'm amassing this, all this material that then I can actually look through. I mean, I shot the material for the films, and I looked at them aesthetically, and like I said, I try to edit them to the music. But now for these science lectures, I actually can go through my footage and say like, oh yeah, pulsating auroras. I know. Oh, these are something that also I'm starting to read about, which are some dark streaks. They call them dark auroras. So I'm still investigating the origin of that. So let's look at a clip of a substorm with music by John Estacio. This would be Borealis, the second piece in the triptych. Speeding it up. And then, so sometimes the auroras throughout the night, they go from, kind of like quiet, and like, remember I told you that there's a correlation between being quiet and still and the brightness, which for a photographer, the correlation is just perfect, because then that means that I'm taking long exposures because it's faint, so I need to collect light instead of like for 2 seconds, I'm collecting light for 10 seconds, but I don't want to lose motion, right? I don't want to lose temporal frequency. So that's okay, because in 10 seconds, they're not changing much. But as they become brighter, then I have to increase the sampling frequency. I have to take shorter exposures, which is great, because there's so much light that the exposures have to be short. So this is from Borealis. And again, so here, what I was just telling you about editing to the music, so what I'm doing is I'm editing the brightening of the aurora and correlating it to the Okay, and from Borealis as well. Oh, here what we're seeing is from discrete sources, discrete auroras to the diffuse aurora. So notice how they're getting more diffuse, wispy. It gets. And that can actually, so that can happen a couple of times during the night. It can go from, discrete to discrete again. You get those substorms, and then diffuse again. And it can go until the morning hours. Okay, so again, all of that is time-lapse photography, but one of the most common questions that I get during the talk is like, okay, so that's time-lapse, it's sped up. How fast do they actually move? Okay, well, when they're quiet, it's like slow-moving clouds, right? You barely can see the motion. But during the substorm, they can move this fast. So this is real-time video with a Nikon, for you photography buffs, with a Nikon D5. Now, look how fast that is moving. Now, imagine seeing that with your own eyes. And you can see the green, and you can definitely see that lower red. It's completely noticeable to the human eye because it gets so bright. Look, that's looking straight up. Okay, so then the velocities of that lower edge can be up to 20 kilometers per second. Okay, so that happens, and they're very the propagation itself, the disturbance. The disturbances have a very, very short lifetime. So it's very difficult to just follow one along the way because they last for a few seconds, but look how fast they move. So this usually lasts for a few minutes, and this, by the way, is from last September. There was a night that this event lasted for about 20 minutes. And I know that because I have the video to prove it. I just kept on shooting. And by the way, again, for those of you interested in the photography, this is with a new Sigma lens that it's 14 millimeter, but f1.8. So it's 2 1/3 or 1 1/3 times faster than 1.3 EVs faster than the 2.8 lens. And then the Nikon D5 pushing the ISO to 52,000. And again, it doesn't look as beautiful as the time lapse because I'm integrating for a longer time. But for demonstration purposes, it's just perfect. Now, so the other question is, what about the colors? Do they look like that? So here I'm using photo editing to actually desaturate and make the image as less bright to mimic the human eye, or what I think it's what I perceive when I'm there. So you'll see the green is going to be a faint green. You'll see the color. The red is barely visible. Sometimes when it's really bright, then you can get the red above. And then, of course, like I said, the lower red is completely visible. So this is more or less what you see. The motion is completely perceptible, but then with photography, you get something like this. So this is not, this is what the camera is capturing. Okay, it's simply capturing more light and more color. And what happens to the human eye is that we have evolved, our eyes and brains have evolved in such a way that during the day, on the retina, the cones are the ones really active because those are the ones that distinguish light, can perceive light. And then the rods are the ones that kick in at night because it's more important to see levels of brightness at night more than color. So, and this is something that, if you think about it, you realize that it's difficult to see colors at night, and it's not necessarily because it's dark. It's because those cones are not working. Now, when the level brightness goes above a certain threshold, and then you can see those colors. But again, the camera doesn't have that problem. So, like I said, I'm gathering all this material for the films and for the lectures. But actually, NASA has a program. I'm sure you know about citizen science, right? Where citizens can make some kind of observation or some work on their computer and contribute to scientific research. So there's a program called Aurora, where when you spot the northern lights, and actually from Michigan you can see the northern lights about 10 times a year, according to the project, you report about it, and then you get notifications about the aurora. So you can go outside and make your observations from your location and then report on those observations. So there's, for example, an astrophotographer captured these unusual auroral beats and then contributed that. So, right? So the aurora researchers are not looking at just like astronomers, they're not looking at the sky the whole time. So people on the ground with their cameras can actually contribute to the science. Something that has been in the news recently is this arc that apparently it's actually thermal emission. Okay, so it's because the gas inside the stream is much hotter than the outside, and it's emitting light, not what we explain, the line emission and the cascading electrons, but actually thermally. It's because of heat. And so this photograph, actually the credit goes to a friend of mine in Calgary. His name is Alan Dyer, excellent astrophotographer. And it was the aurora photographers in Calgary, in the Alberta province, that actually posted photos like this one on Facebook, and that got the attention of aurora researchers. And Dr. Eric Donovan at the University of Calgary started studying this, and he's about to publish a paper where he's going to explain what the mechanism in charge is. It seems that it happens. You see, here you see auroras to the north, and the object named Steve to the south. Now, you might be asking, why calling it Steve? Well, obviously, these aurora photographers have a sense of humor, and the name comes from this animated movie.
What is this thing?
Heather, no!
I'm scared. Me too, Mama.
Shh, shh, it's okay. It's just, what is this thing, Lou?
Well, it's Vern?
Well, it's obviously some kind of bush.
I would be a lot less afraid of it if I just knew what it was called.
Let's call it Steve.
Steve?
It's a pretty name.
Steve sounds nice.
Yeah, I'm a lot less scared of Steve.
Oh, great and powerful Steve! What do you want?
So that's the origin. So that's a good sense of humor. And the name has stuck so far. I think I saw somewhere an acronym where they actually now want to turn Steve into actual scientific acronyms. And you know that us scientists, we love acronyms. So then let's talk about, see how we're doing on time. Yeah, that's fine. About Yellowknife. So why Yellowknife? And I've been to some of these places, but I recently, these other places that I showed you at the beginning of the talk, but I recently talked to a raw photographer who has been doing this since the 90s. And he tells me that he's been to all of these places, and Yellowknife he thinks it's the best place. And so geographically speaking, it's obviously in a favorable position with respect to the magnetic field, because and this, I can, can be a witness to this claim that if the skies are clear, you're going to see northern lights. So I have been to Yellowknife. I have had 42 observing nights, and not a single night have I gone out when the sky is clear and I haven't seen auroras. So if I haven't seen auroras, it's because the skies are too cloudy for the auroras to be seen. Sometimes you see them through the cloud, in between the clouds, through the breaks, and you can get beautiful photographs. And I have photographs where it's cloudy, but then the clouds are green because they're not thick enough, and some light seeps through the clouds. So most of Northwest Territories, and of course Yellowknife included, is under the aurora oval. So basically, you want to avoid the summer months because, again, daytime is so long, so you get a very short twilight. It's relatively flat, but of course, I don't want a place that it's so flat that it's boring for my photography. But it has, hills and the boreal forest. I'll show you photos. So it's interesting enough for my photography, but at the same time, I don't want a really tall mountain right in front of me blocking the auroras. And population 19,000, so I drive like 40 minutes outside the city, and it's dark enough. So because of that, that's why I'm taking people to see the lights. And what happened is that after 3 films, I was like, I cannot continue making films about the northern lights. I mean, it is 3 words. So, okay, so I have to now find out a way to, an official excuse to continue going to Yellowknife. And I said, you know what? I can extend this whole project about, science communication by then taking people, and then, they would get a lecture like this one, so they get to learn about the auroras. And if they're interested in photographing the lights, then they can do that as well, because I'll teach them. And I had the first official group last September, and the plan is to go every September and every March. So this, of course, now I'm doing also drone photography. So the interesting about the Legend of the Northern Lights, which was shot in the winter months, it was done from this point on an ice road. So I'm in the middle of the lake, open sky. So I said, you know what, I have to photograph this from above. So I shot this in September. That's how part of Yellowknife, looks like. It's a beautiful place in September as well as in winter. So we have bike tours, and every time I go, I find a new spot that is beautiful for the photography. So again, drone photography, taking pictures of what's called Cameron Falls, and then this is what you want to see, right? And then, so, and again, and most of my photography, that's what I do, right? I don't want to just photograph the sky. I want to photograph the sky in the context of where I'm photographing it from. And you'll see that that's a common thread in my wide field photography. And of course, you saw the reflection on the snow, but then in September, you'll get the reflection on the water, which is beautiful. And then we get to learn about the Dene First Nation people, dog sledding, and then, of course, the photography in the middle. That's what I was telling you about. That's in the middle of the lake. Now, from me, from my perspective, you know, I'm originally from Puerto Rico, so you can imagine how bizarre it is to be standing on. So when they told me the first time, have you been on a ice road? I said, I guess so, like an icy road? No, this is not on ice. This is not, you know, it's not ice and pavement. This is ice and water. So, but it's fantastic. It's a fantastic place. A stack of images showing the rotation of Earth. We access to the best outhouses in Yellowknife. Look how it's just beautiful. Just beautiful. So most of this photography, if you Google my name and get to my Flickr account, you'll see all these photographs. So I was telling you about the clouds and, you know, the breaks in the clouds. So there's all sorts of photographs that, you know, unfortunately, we don't have time to go through them. But we have time to do one final thing, and that is show you the last part of the Aurora triptych, Wondrous Light with Music by John Estacio. work on bringing this film to the Hill Auditorium. Thank you.